Hello everyone and welcome back. So in this video we are going to discuss about Simpson's rule. In fact, we are going to derive a formula for Simpson's rule. Now deriving the formula is no easy task. Okay, so bear with me, be with me until the end of this video. Now what is Simpson's rule? Well, for all the other methods that we learned before, we use rectangles or trapezoids to cover up the region that we want to calculate area, right? So if you want to approximate the area of this region, if you're using one of the previous methods, we use either rectangles or trapezoids. Now, how about other possibilities? Can we use other polygons or something else? Well, the Simpson's rule is about using parabolas instead of rectangles or trapezoids, okay? So let me show you. The way we start the Simpson rule is same as other methods. We have the interval going from A to B, so let's mark that. And let's find the width. So we use the same old formula. Delta x is b minus a over n. N is the number of subintervals. Now here we don't have rectangles. We can say number of subintervals is n. Okay, so this is the width. Now let's mark them here in our picture. Okay, so we have these subintervals. Let's label them x0, x1, x2, so and so on, xn. Now, as I said, we will use parabolas instead of rectangles or trapezoids. Now, here's the thing. One difference with Simpson's rule is that to create a parabola, we use two subintervals. Now remember the other methods. So in other methods, we had a one rectangle in each subinterval, right? Or a one trapezoid in each subinterval, right? We use only one subinterval at a time. But constructing parabolas, actually we have to use two subintervals. I'll explain it to you later why we have to do that. So what I'm going to do is so the way we create these parabolas is that let's focus on the first two subintervals. So we are going to use x0, x1 and x2. Let's mark them here because we need them. Oh, come on. Okay, x0, x1, x2. So this is a combination of two subintervals, right? So I'm going to create a parabola over it. The way I'm going to create a parabola over it is that this parabola will intersect the graph at these 3 points, of the function. Okay, so it's gonna behave like this something. I'm not the best artist, I'm sorry about that. Now you can already see why Simpson's method is one of the best methods, okay, because it's gonna follow the shape of the curve. It's gonna resemble it better than rectangles or trapezoids. Okay, all right, so assume this is a parabola and we have a one parabola covering two subintervals, and one special thing about this parabola is that it's gonna cross the graph, intersect the graph f at 3 points. At what are the 3 points? 3 points in the subinterval. Okay, because when you have two subintervals you will have 3 points like here. Okay, and the parabola will intersect the graph at these 3 points. That's a crucial fact, that's why I'm repeating it. Okay, one important thing, in Simpson's method, n has to be even. Now, can you think why? Pause the video and think. I think you will be able to guess it. Now, think about this. We create parabolas in every two subinterval. Okay? So, if n is odd, for example, if you have 7 subintervals, so in the first two subinterval you have a parabola, second two subinterval you have a parabola, third two subinterval you have a parabola, now you are left with a one extra subinterval, right? So what are you going to do with that? You cannot do anything. So because of that, when we use Simpson's rule, we have to make sure that n is always even. It has to be even. Okay, so n is even, and the reason is that we create parabola using two subintervals. Okay, all right, now the next question is that, well, you know why we use rectangles and trapezoids in previous methods? Because it's so much easy to find the area in a rectangle, right? It's the length times width. But how about in a parabola? Now anyway, you have to calculate the area under this parabola. How are you going to do that? Is there a formula? Now think about this. what is the equation of a parabola? How would you write a parabola generally? It's going to look like capital AX square plus capital BX plus C. This is the formula of a parabola. Okay? Alright, this is how it looks like. Now, if you want to find the area under the parabola, now this is a simple function that you can integrate, right? So if you integrate this equation from x0 to x2, for example, you will get the area under this parabola exactly, because you don't need approximate integration here, okay, because this is a very easy integral to solve. So we will integrate from x0 to x2. That's the idea. It will give you the exact area, okay. Now one more thing. Here's the thing. Now to make our integration easy, okay, computation, simplifications easy, what I'm going to do is I'm going to relabel these, redefine these subinterval points. I'm going to label this x0 as 0 and x1 as delta x, because it's delta x away, right? And guess what? How long away x2 is? That's 2 delta x away, right? So we are actually integrating from 0 to 2 delta x. So this will make my life easy. Not 2ax, 2 delta x. Okay, so let's integrate. Okay, you will see. Now if you integrate ax square, you will get ax cube over 3 plus bx square over 2 plus cx. Now you want to evaluate this from 0 to 2 delta x. Now let's substitute 2 delta x. So if you substitute 2 delta x to the x, what you're going to get is, let me simplify that. Let me do that really fast. So you're going to get 8a. Okay, 2 cube is 8a delta x cube over 3 plus 4b delta x square over 2 plus 2 delta xc minus, now you have to substitute 0 for x. Now if you substitute 0 for x, what you're going to get is 0, right? Because everything is multiplied by x is 0, so that's gone. So if you write the area, okay, so 4 and 2 cancel out. That can be simplified. 2b delta x square plus 2 delta xc. Now this is the area under the parabola in the first two subintervals. Okay, alright, let's save it. Now one question you may ask is that, well, this is the area under the first two subintervals. How about the other subintervals? Here's my goal with this method, the formula derivation video. What I'm going to do is I'm going to get a formula for the area under the parabola in the first two subintervals, and it will have some pattern that we can see, and using that pattern we can find the area under the whole parabola that's approximating this curve. Okay, so that's the idea. So let's find the area under the first two subintervals, and then the rest will come along. Okay, all right. Now if you look at this area, this is not a good formula. This is half derived formula, because we don't know what is A, we don't know what is B, we don't know what is C. So we have to figure out A, B and C. Now what are A, B and C? A, B and C are the coefficients of the equation of parabola. Now how can we find A, B and C? Now here's something I said, a crucial fact. I said this parabola will cross the graph at the three points of the subinterval. Okay, so 3 points are x0, x1 and x2. So the parabola will cross the function at these 3 points. That means if you substitute x0, okay, so if you substitute x0 for x here, you would get fx0 out of here, right? So x0 is actually 0. We defined it to be 0, right, with our new labeling. So if you substitute 0 for x, these two are gone. So C is fx0. Okay, so x0 is actually 0. So if you substitute x0 for x, this g value should be equal to the function value, function value at x0. So that's why I have fx0. Okay, and when you substitute x0, well, x0 is 0. We relabeled it, so these two terms will go away and c will be fx0. Okay, all right. Now let's use the point x1 to find a and b. So if x is x1, the function value is going to be fx1, and the parabola is a. Well, x1 is actually delta x, right? So it's going to be delta x square plus b delta x plus c. We already know fx0. Now let's simplify this. Let's take fx naught to the other side. So let's factor delta x out from here. So a delta x plus b, and this is fx1 minus fx naught. Now from here we can divide by delta x, so we get a delta x plus b as fx1 minus fx naught divide by delta x. So this is a one equation, because we cannot solve for a and b here, right? Because we have two unknowns. Now let's use the other point. Remember, we have another point. Let's use x2. When x is equal to x2, the function value is going to be what? Fx2, and x2 is actually 2 delta x, so let's substitute 2 delta x here. So it's going to be 4 delta x square a, because if you substitute 2 delta x here, it's going to be 4 delta x square plus 2 delta x b plus this is fx naught, right? Let's simplify. Let's take fx naught to the other side and let's factor 2 delta x out. So it's going to be 2a delta x plus b is going to be fx2 minus fx naught, and let's divide by 2 delta x. So this is what we get. All right, perfect. So this is the second equation. See, we have two equations now. Okay, two unknowns are a and b, and two equations. Now let's solve these two equations simultaneously to find a and b. The way I'm gonna solve these two simultaneously is that I'm gonna subtract equation 1 from equation 2. So 2ax minus a delta x is going to be a delta x, right? And b cancel out, that is why I subtract both of them. So we have to subtract fx2 minus fx naught by fx1 minus fx naught. Oh, this is going to be fun. Now be careful, let's have a bracket here just to make sure we do not mess up with negative signs. So for the common denominator, so here 2 delta x, here delta x, so let's multiply everything by 2 here. Okay, so this is going to be 2, this is going to be 2, let's have that bracket. Let's simplify. 2 delta x, fun, fx2, that's fx2 alone itself, minus fx naught, minus 2fx1 plus 2fx naught. Right, so this is what we get. If we simplify it furthermore, this is fx2 minus 2fx1, and these two simplified will give you fx naught. Okay, and this is divided by 2 delta x. This is a delta x. So let's take the delta x to the other side. It's going to be delta x square. This is my a. Okay, all right, we found a. Now let's use this a to find b. Now what we can do is, let's write the one equation involving b. Well, we know a delta x plus b is fx1 minus fx naught over delta x. Let's make sure that it's clear, otherwise I have to remake this video. Okay, now let's use this a from here to this equation, substitute that a into this equation, and let's find out b. To make my simplifications clear, let's do this slowly. Fx2, so I'm substituting a that I found in the previous step, okay, in the second equation, 2 delta x square, and multiply by delta x plus b is equal to fx1. Hopefully this will simplify and give me a nice simple formula. 1 delta x cancel out, so it's going to be b equal to fx1 minus fx naught divided by delta x, subtract, so I'm going to bring this whole thing into the right hand side, fx2 minus 2fx1 plus fx naught divide by 2 delta x. So that's what I have. Let's see, the common denominator 2 delta x should be 2 delta x, so multiply this everything by 2. So b is going to be 2fx1 minus 2fx naught minus fx2 minus plus 2fx1 minus fx naught divided by 2 delta x. Let's see what we get after simplification. B is 2fx1 and 2fx1. It seems to be like it's 4fx1. Nice. minus 2fx naught minus fx naught, 3fx naught, nice, and minus fx2. Okay, seems to be like this is B. Okay, so we got both A and B. Shall we write down A close to B? Okay, let's open a new sheet. You know what? Let's open a new sheet and copy this A, B, and the formula of the area into a new sheet, because if I do everything in this same sheet, it's going to be a mess and it's going to be ugly than this. Okay, so we have all the formulas in a new sheet. So this is the area under the parabola in the first two subintervals. Okay, just under the first two subintervals. Now we know the formula for A, B, and C. So let's substitute A, B, and C into this big formula to figure out the area under the parabola within first two subintervals. Okay, let's do this really carefully. So it's going to be 8 over 3. A is fx2 minus 2fx1 plus fx naught divided by 2 delta x square times delta x cube plus 2 delta x square. B is 4fx1, let's make some space, minus 3fx naught minus fx2 divided by 2 delta x, so that's B, and 2 delta xc. C is this, yes, that's fx naught. Okay, now delta x square cancel out and some terms will left, 2 cancel out, so what's left? So it's going to be 8 over 3, so 2 and 8 cancel out. It seems to be like we get 4 here, so 4 over 3 fx2 minus 2fx1 plus fx naught times delta x, because 1 delta x will leave after cancelling out. Here also 1 delta x will leave, will be left. So this is what's left here, minus fx2, and also here 2 delta x fx naught. Now if you look at all three expressions, we can see delta x is common, right? We can factor out a delta x. So if you factor out a delta x, and let's see what's going on. We have 3 here. Let's make the common denominator 3 by making denominator 3 here and numerator 3 multiplying by 3 and dividing by 3. So we can take a 3 out too from all these 3 denominators in the 3 expressions. So it's going to be 4 times fx2 minus 2fx1 plus fx naught, and plus here we have to multiply by 3, 4fx1 minus 3fx naught minus fx2. Okay, here 3 times 2 is 6 fx naught. Okay, all right, I hope that's correct. Okay, so what I did basically is, I factored out 1 over 3 out and delta x out. So what we are left with only the numerator terms. Here the numerator is 3 times 2. Here the numerator is 3 times this big expression. So let's simplify this. Delta x over 3. Let's see what we get. If we multiply through 4 here, okay, 4fx2 minus 8fx1 plus 4fx naught. Here 12fx1 minus 9fx naught minus 3fx2 plus 6fx naught. Okay, let's simplify. We are on the last step. We are almost done. Let's count x2 terms. So 4x2 minus 3x2, that's all, right? So that will give you just fx2. Minus 8fx1 and 12fx1 will give you what? 4fx1. Okay, yes, 4fx1. And then x naught will give us 4fx naught minus 9fx naught is minus 5fx naught plus 6fx naught will give us fx naught. Okay. All right, so this is the formula. So the formula is, let's rewrite this, fx naught plus 4fx1 plus fx2 times everything times delta x over 3. Fantastic. So this is the simplified area under the parabola within first two subintervals. Okay, let's continue our work in a new sheet now. Let's quickly recap what we have been doing here. So in Simpson's rule, we are going to approximate the area in this region using parabolas. So what we did is we took this big interval from A to B, we divided it into n subintervals. Remember, n has to be even because we are gonna actually use parabolas to approximate the area in this region. So the way we create these parabolas is that we have a one parabola for every couple of subintervals. Okay, so we use two subintervals to construct a one parabola. That's why n has to be even. Okay, now what I did so far is that I took the very first two subinterval. Okay, so the very first two subinterval is x0, x1 and x2. Okay, so there's a parabola above these two subintervals. So we found the area under this parabola between the first two subintervals, right? So this is the formula for the area for first two subintervals. Now we have to find the area under the first two, under the second couple of subintervals, third couple of subintervals, so and so on, right? But it was a lot of work even to get this formula, right? What we are going to do from here is we are going to look at the pattern and we are going to construct the formulas for the areas under other parabolas under other subintervals using this area formula under the first two subintervals. Okay, if you look at here, the formula is delta x over 3 if you follow the pattern. So we are constructing the area for the second pair of subinterval. So the second pair of subinterval is x2, x3 and x4, right? Now look at this. This formula says the function evaluated at the first point of the subinterval. So function evaluated at the first point is x2 plus 4 times function evaluated at the middle point. So here middle point is x3. So fx3 plus the function evaluated at the last point, right? That is why we have fx2 here. So the last point of the second pair is fx4. That's how you get the formula for the area under the second pair of subinterval. Third pair of subinterval is actually going from x4, x5 and x6. So then the formula is delta x over 3 function evaluated at x4 plus 4 times function evaluated at x5 plus function evaluated at x6. So this is the formula. Okay, all right, now let's look at the final pair of subintervals. So the final pair is xn is the last point, xn minus 1 is the point before that, and xn minus 2 is the first point of the last two subintervals. So the formula will be delta x over 3 function evaluated at the first point xn minus 2 4 times function evaluated at xn minus 1 plus function evaluated at last point. Alright, now let's add them up. Now if you add them up, you have to look at this here. There is a very clear pattern. Delta x over 3 is common, right? So if you add all of them to get the total area, we can factor out delta x over 3. That's okay. Now if you look at this, fx naught is the only is appearing only one time in all these formulas, right? So that comes up for us, fx naught. Plus if you look at carefully, look at this, look at the the points that are evaluated where you have coefficient of 4. So x1, x3, x5 and xn minus 1, they have coefficient of 4. The common thing between them is that their index is odd, 1, 3, 5, n minus 1. N is even, so n minus 1 is odd. So every odd index will have a coefficient of 4. Okay, and look at this, the index with even 2, 2, 4, see 4, they appear twice. Here you have fx2, now you add fx2 to this, so there will be 2 fx2s, there will be 2 fx4s, so there will be couple of terms from odd index function terms, right? So there will be 2 times fx2 and 2 times fx4, 2 times fx6, so likewise. Okay, So the pattern continues, this goes on, and the last point, the very last point, that appears only one time, fxn, and the term before that is odd, so the coefficient is 4, so 4fxn minus 1. This is the formula. Okay, so the formula to approximate this integral, definite integral, using Simpson's rule, we can easily memorize it. Okay, so the function evaluated at the first point, then the pattern is 1 4 2 4 2 4 2 4 2, likewise. Okay, so 4fx1 plus 2fx2, okay, plus blah blah blah, and 4fxn minus 1 and plus fxn, the very last point doesn't have any coefficient. Okay, so this is the formula, and I think I showed you how I think I clearly showed you how to derive this formula. I hope that it's clear. Okay, so yeah, there you go. It was a tedious to get this formula, tedious calculations, but if you think carefully, it all makes sense. It's slightly different from what we have been doing so far in the other approximate integration methods. Okay, so the pattern should be very easy to remember, and the last point will not have a coefficient. Well, the coefficient is 1, and the point before that will have coefficient 4. So 1 4 2 4 2 4 2, so 4 2 switches. Okay, all right, so in the next video I will solve a simple example from Simpson's rule. Okay, thank you.